Okay, so today's lesson, section 3D-D, we're talking about quadric surfaces. Now, a quadric surface is a surface that if the graph in 3D is going to be to the second degree. So all your powers are to the second power, for the most part, or the highest degree is second power. Okay, and that would end up being quadric surface. Now, the difference between a quadric surface and a cylinder is that you're going to have all three of your variables in your equation. So you're not missing something that just becomes whatever it wants to be, so it makes an infinite plane, basically. Here you're going to have all three variables, so then we're going to get different traces or cross-sections in our planes that give us some interesting pictures. So the cross-sections of the quadric surface are going to either be conics, so they could be parabolas, ellipses, circles, hyperbolas, or they're going to be degenerates, so they could be a point, an empty set. They could also be a line or two lines, depending on what we get. Okay. Now this equation that I have written down here is the general form for a quadric surface. We're not going to have any of those, so don't worry about having to be able to put that into standard form. Your equations are going to mostly look like this. Or this. Okay, so one of the two purples. Now, the one on the top is called a central quadric. That means the center is at 0, 0, the origin. The other one is not like your center is not there, but this is actually like one of our pictures that we have is a hyperbolic paraboloid. And so that's kind of what it would look like. Also, you have other pictures that they would end up being. Like you could have an elliptical cone from the one on the bottom. And so I'll show you pictures of that. But so just so you know, those are the two types of equations that you're going to kind of run into. Okay? Now, another thing to talk about with quadrics is something called a surface of revolution. So each surface can be rotated on a fixed line, which is called the axis of the surface. Now, that has different words, like it's always going to have the word axis to it, so remember that one, but it can be described as the axis of rotation or the axis of revolution. So axis of surface, revolution, rotation, they're all the same thing. It's just this line that you can rotate your picture around, and what you're going to look at is it's going to not change, basically. So it looks symmetrical in all rotations. So if a given surface has cross-sections that are perpendicular to the axis of the surface and are either, okay, so one of these three things are either a circle, a point, or an empty set, then the surface is called a surface of revolution. So basically, if I can take a shape and rotate it around, and it has one of those properties like all the time, so if you cut it on like a plane perpendicular to this axis, and you got a circle, and then you cut it another place, you got a empty set or a point. But you always get one of those things, not all at the same time, but one of those things for each cross section, and then it's a surface of revolution. We'll try to show you what we mean in class, because it's hard to make. You can't make anything rotate on this video, but we'll try to do that as best as we can in class so you can understand what that means. Okay, now here are some examples of our quadric surfaces. So the first one we've graphed before, it's called a ellipsoid. Okay, so that means all the cross sections for xy plane, the xz plane, and the yz plane are all ellipses. Okay, so it's ellipse all the way around. Okay, now on the right here I put SOR, so surface of revolution. I put down when it would end up being a surface of revolution. So if A, B, and C in your equation for the ellipsoid are all the same, so that would make it a sphere, then that would make it a quadric surface, or a surface of revolution. But actually, when you do that, then it makes it a surface of revolution on all your axes because it's a sphere. Okay, so that's just one possibility. Okay, for a hyperboloid of one sheet, you have this little picture. So it kind of looks like a cylinder, but the middle is like, think of like you take a string and you like tighten it, and so the middle is skinnier than the top or bottom, but that's what a hyperboloid of one sheet would be. So that means that like you have a set of hyperbolas in one plane, and then if you look at the other plane, like they're kind of all at the same angle, then you have another set of parabolas. So you have like two sets, and then the other plane could be an ellipse. It could also be a circle. Okay, but that's what your cross sections would be for that. And your equation is above. If it's a surface of revolution, A and B must be equal to one another for that to be the case. So basically making a circle in the middle as you rotate around the axis of rotation. A hyperboloid of two sheets. Now I know my picture looks kind of funny. Now keep in context that my 3D grapher can only do it in a certain like value, like it only has a certain window, I want to say, and so that's why it kind of looks like it's cut off. It looks kind of weird. It's not a bowl shape because the edges are kind of truncated, if you will, and so that's why it kind of looks like that, because it can't show everything. So then you have two hyperbolas here as well, but then in the YZ plane there's nothing, so it's empty set, so that means it's breaks. So the reason why the first one's called a hyperboloid of one sheet, because you could make one sheet of paper like and to make that picture, so you could make one entire surface so there's no disconnect between the two surfaces or the two hyperbolas. Okay, the other one is two sheets because you would need two pieces of paper, kind of like to show it, or you have two different surfaces to create this picture. It's not just one. So that's what they mean by one sheet and two sheets. Okay. The next one is and then for the hyperboloid of two sheets, to be a surface of revolution, B and C must be equal to one another. An elliptical paraboloid has that certain equation. So then here, in a cross section for XY plane, you have a point. Your XZ and YZ planes both are parabolas. And so here, for it to be a surface of revolution, it would have to be A equals B. For the hyperbolic paraboloid, now this one's kind of a funky picture. You won't have this very often when we graph things, but because it's kind of hard to graph in essence. But you've got parabolas working together, but then you don't really have a hyperbola per se, okay? But you do have intersecting lines that create that kind of weird shape. It's kind of almost like a saddle, and so maybe if you get down the road and you want to be a mathematician in college, one of the topics you could talk about or go into is hyperbolic geometry, which most of your surfaces are kind of look like that, where it's kind of just undulated, and it doesn't really have a uniform surface all the way around. Okay, but here, this one, you cannot have a surface of revolution, so it never works. It doesn't matter what A, B, or C are. Okay, and then the last one I want to show is the elliptical cone. Okay, here that XY cross section is a point, and then you have some other degenerate conics going on, so intersecting lines to create this. And then if it's surface of revolution, it would have to have A and B be the same. Okay, so those are some examples. Those are the main ones that we'll talk about. There's not really any others that we'll come across that are important for you to know, but just make sure you have those equations so you can kind of identify what those are. Okay, so here, for example 1, I want to be able to find the traces and determine if the graph is a surface of revolution. And if it is, I want to identify the axis of rotation or axis of surface. And then graph and label at least 3 points for each equation. Okay, so here I have an equation. Now I need to be able to put it into a kind of a standard form. So I'm going to divide everything by 36. So once I do that, I can reduce. So x squared over 9 minus y squared over 4 minus z squared over 4 is equal to 1. Now here, looking at my equations that I was just talking about, this one, because you have an x squared that's plus, y squared is minus, z squared is minus, this one would fit into the hyperboloid of two sheets. Okay, so it's kind of have two bowl shapes that are reflections of each other's, kind of, and so they're looking in the opposite direction of one another. And now also, if B and C are equal, which B and C are both 4, okay, therefore that means that now they're both like -4, or +4, however you look at it. That means that this is the surface of revolution. And so now identifying the axis, it's always going to be the one that's not involved. So because B and C are underneath your y squared and your z squared, that means that x squared is like the odd man out. So it's the axis that you're going to be rotating around and keeping it perfectly the same. So surface of revolution, you would say yes, and then axis of rotation or revolution is the x-axis. Okay? Now I want to be able to identify the traces, so I can kind of graph these. So the xy plane. Now, usually to identify these, if I just look at them, I cover up the variable that I'm not talking about. So if I'm talking about the xy plane, then I cover up z to look at what my equation would be in 2D almost. So here I'd have x squared over 9 minus y squared over 4 equals 1. So then that would be a hyperbola. Okay, for the xz plane, do the same thing, cover up the y, so that would also be a hyperbola. And then for the yz plane, I would cover up the x, and then here, because you have a negative and a negative, that doesn't fit into anything for 2D, because you can't have two negatives, so then that would actually be one of our degenerate cases. Another way of thinking about it, if you divided everything by -1, that would make your 1 on the right side negative, and you can't have a -1 over there. So that would be the empty set. Right? So then now I can kind of graph these in their certain form. So for my xy plane, I want to graph my hyperbola, so go out to 3 and go down by 3, and then for my y, I'm going to go out by 2 and out by 2. So then now I'm making my central box, so I can write my asymptotes here. Okay. Here's 1. And then here's the other. Move this up just a little bit. Okay, so now I can draw my, how about let's make them a different color, just so it's easier to see my hyperbolas. Okay, so then now I want to graph the XZ plane. So let's pick a different color again. Green. So if I go, I still have the 3's already ready for the X's, and then Z, you go up 2 and down 2, and so now okay, so there's that one, and so now the only bad thing about doing the central box for these is that there's so much going on that I can't really see my stuff. Let's choose the same color for my hyperbolas. But I guess when you do this, you will have the ability to do lightness. So I would suggest making your hyperbola or your any of the extra stuff that's not your graph. So like doing the asymptotes, the central box, try to do it as light as possible, and then make your other stuff super dark, or use a different color when you get to that part. Then it'll make it easier to see. Here I'm going to try to make these bowls. Now, I'm not going to graph the YZ plane because it's empty. There's nothing there. There's nothing connecting them, so I don't have to. So now I'm going to make my bowls, so I kind of try to make a circle that does that. And so you can do your shading. You might be a lot better than me at shading, which is not hard to do. Okay, so then there's another bowl, and that's my best guess of how it looks. Okay, I have it over here on the next slide. So example 1A should look like that technically. Okay, so it looks a bowl like two bowls facing the opposite direction of one another. Okay, so that's what we should get. So that's what I'm going for. That's why the 3D grapher is nice, to help you can like kind of put that in perspective, so you can kind of organize your thoughts. Now you got a sneak peek at 1B from that last slide, but here, same thing. I want to get everything equal to 1. Okay, so that gives me x squared over 24, y squared over 16 plus z squared over 12 equals 1. So here, because everything's plus plus plus, that means we have an ellipsoid. Okay, and none of them match. So like A doesn't equal B, doesn't equal C. So when we say surface of revolution, we would say no, it does not. Okay, and then we're done with that. So now I want to do my traces. Oops. Okay, so for the XY plane, since it's ellipsoid, it will be an ellipse. For the XZ plane, it's an ellipse. And then for the YZ plane, it's an ellipse as well. Okay, so now I want to graph it like I did previously. So 24, the A value would be 2 squared of 6. And I did this on my calculator earlier, so 4.89. Let's do 9. Okay, B would be 4. C would be 2 squared of 3, which is 3.5. Okay, so then just kind of try to plot them as best as you can. So for my A's, and that's on the x-axis, so I go out 4.9. Okay, and then for my B, go on the Y, so 1, 4. And then C would be 3.5. So 1, 2. Okay, now I'm just going to try to connect all my points with my lines. I'll try to stay with one color, see if how this looks as well. So with my XY plane, and then my XZ plane, and then my let's try that one again. Okay, and so you can try to do your traces or like contours, as what the 3D grapher does, making lines so that you can kind of get the shape better. Or you could just leave it like that, or work your magic and shading. But this is what they should look like. For example, 1B. It's just an ellipsoid, but it's hard for us to be able to draw in 3D because we don't have a 3D grapher like on our paper. It's just 2D. So we're trying to take a 3D picture and put it on 2D, which is hard. So don't worry if it's not perfect. I just look at the vertices and kind of get the traces. And so if you know what your traces are and what it should look like when you label stuff, then you should be good. Okay? I'll be able to tell what you're talking about. Okay? Sorry that's so long, but have fun.